Let's take a look at an example involving matched pair. So in this problem, I have reading and writing scores for the same 200 students. And this was a study done by the National Center of Educational Statistics. And they conducted a survey of high school seniors collecting test data on reading, writing, and several other subjects. And we have a random sample of 200 students from the survey with some side-by-side box plots, as well as a histogram looking at their differences. At first glance for this histogram, I'm noticing that it does appear to have a center pretty close to 0. Now, if the center is 0, this is telling me that my reading and writing scores would be roughly the same thing. Like if I had an 80 for reading and an 80 for writing, 80 minus 80 would give me 0. So a difference of 0 would mean they're equally good for reading and writing. First question that I have in here, and then we'll go through this hypothesis test, is are the reading and writing scores of students independent? And I would say that they are definitely paired. And there are a couple reasons why I would say these things are definitely paired. First off, they're the same students. Your reading score also would affect your writing scores and vice versa. So I've got information that is paired and it's paired in a meaningful way. So yes, because they're two different activities, that's not enough. So two different activities doesn't make them paired. No, they are paired since have a reading and writing. Nope, that doesn't make sense. I would say students are independent, and yes, they are paired since each student has both a reading score and a writing score. Create the hypotheses here. It's giving me the average observed difference in the scores for reading minus writing is negative 0.545. The standard deviation of the scores is 8.887. And it asks, do these data provide convincing evidence of a difference? Okay, a couple of reminders before we get too far into this. First off, it's telling me here that I'm looking at 200 students. I'm calling that K because I have 200 pairs. So in total, I would have like 400 pieces of information. 200 reading scores and 200 in writing scores. It wants me to perform a test for a difference. And it's given me some preliminary information. It says the average difference, reading minus writing. And I like to use the letter D for difference. But reading minus writing was negative 0.545. And the standard deviation for the differences was 8.887. It's looking for the test statistic, p-value, conclusion. Let's blow this page up and do the 4 steps of a hypothesis test together. First step. My null hypothesis is going to be that the average difference is equal to 0. And this would represent there being no difference in my two groups. Alternative hypothesis. It doesn't say reading better than writing. It doesn't say writing better than reading. I'm testing for a difference. So I'm going to have does not equals. This would tell me that there was a relationship between those two variables. For the model, I'm going to be using a t-distribution with some degree of freedom. The center will always be 0. That represents no difference. My standard deviation will be the standard deviations of the differences over the square root of the number of terms. And when I'm using this model, my degree of freedom is going to be the number of terms minus 1. I had 200 students, so my degree of freedom is going to be 199 for my model. I have a degree of freedom of 199, a center of 0. My standard deviation was 8.887. My K was 200. I'm going to be looking at sample differences, average of 0, and then that standard deviation, 8.887 over the square root of 200 gave me 0.6284. I'm going to leave it at 0.628. I'm going to match the number of digits they've been using so far, but 0.6284. Third step is my p-value step. And the p-value will look at the likelihood of my sample data. My sample difference here is negative 0.545, or more extreme. This is going to be a two-tailed test. So if I'm drawing my picture out, and this is a t-distribution, but it looks just like a normal curve. In the center, I have 0. And then my observed difference is negative 0.545. And it's a two-tailed test. I'm testing for a difference. So I'm going to shade in both directions. So my p-value is going to be the size of those two tails together. So I'm going to get my t-score here, my test statistic, by taking the value, subtract the center or the claim, divided by the standard deviation. The value I care about is negative 0.545. The center for my model is 0. The standard deviation for my model is 0.628. I'm going to type this into a calculator. Negative 0.545 minus 0 divided by 0.628. And this gives me a t-score of approximately negative 0.868. Or it's a two-tailed test, so I'm going to have the same thing but positive, 0.868. Now I'm going to pause this video for just a second, and I'm going to pull up GeoGebra so we can take a look at that t-score and then the p-value. Okay, here I am inside of GeoGebra. You could use a graphing calculator as well. A lot of different choices here. But I went into GeoGebra. And I'm going to choose the option for probability. And then I'm going to find student for student t-distribution. If I choose this option with these things pointing outwards, it's going to give me a two-tailed test. For my degree of freedom, I'm going to type in 199. So I chose degree of freedom of 199. I'm choosing the shade out direction. And I'm using t-scores of negative 0.868 and 0.868. So both the positive and the negative. So I'm going to type those in. The negative and the positive. And you'll notice that these are the same size. So you could find the size of the left tail and multiply that by 2. You could find the size of the right tail and multiply that by 2. But when I did this, I ended up getting a p-value of 0.3864. And we'll come back to GeoGebra because I want to show you something else that you could have done here to double check your work. But final step conclusion, this is a pretty large p-value compared to a neutral alpha level of 5%, or most alpha levels for that matter. This is certainly bigger than or equal to that number. So we would fail to reject the null hypothesis. If you fail to reject the null hypothesis, this means that we do not have evidence of the alternative, so we do not have evidence of an average difference in reading and writing. So if I fail to reject the null hypothesis, that means I think that value of 0 is still reasonable. And that value of 0 represented there being no difference. So this would be equivalent if I were to make a confidence interval. I would see 0 should be in our confidence interval if we were to make it. I do not have evidence of a difference. I think the difference could be 0. Now, the thing I wanted to show you in GeoGebra as well here is in statistics. If you do a z-test of a mean, this is the same thing that we did before when we looked at one group. You could use an average of 0. We are testing for a difference. The mean that we saw for our sample is negative 0.545. And oh, shoot, I don't have sigma, I have S. So I'm going to use z-scores if I know the population standard deviation, but I have a sample standard deviation. So I'm going to switch over to t-test. I'm using t-scores. My S was that 8.887 number. And the number of pairs is 200. They use the letter capital N. I would use the letter K because it's the number of pairs. This gave me a t-score of negative 8.673. I'm getting roughly the same thing up to a little bit of round off there. And I'm getting a p-value of 0.3868. Let's go into MyOpenMath and type in these results. GeoGebra is a really nice way to double check my work. I'll do it by hand just to get a feel for that process. I'll double check it with technology. Evidence of a difference. So I'm testing for a difference, not greater, not less, different. It's asking me for a test statistic. That's the t-score that I get from my calculation. Negative 0.8, and it says 2 decimal places, so 7. P-value, I got 0.3864. GeoGebra gave me 0.3868. We'll see how much it cares about that rounding. This was a large p-value, so we do not have evidence to reject the null hypothesis. If we did not reject the null hypothesis, and in actuality, the alternative hypothesis was true, the second thing was true, that would be an example of a type 2 error. Incorrectly failing to reject a null hypothesis is a type 2 error. Incorrectly rejecting it, the opposite, is a type 1. Based on the results of the hypothesis test, and a reminder of the hypothesis test, we failed to reject. We do not have evidence of a difference. So that's related to the number 0. We do not expect to see anything meaningful there. So based off the results, would you expect a confidence interval for the average difference between the reading and writing scores to include 0? Oh, great. 0 should be in our confidence interval. So I would say yes, because the evidence was not strong enough to suggest that the average reading and writing scores were different. And going through this looks pretty good. This asks, oops, if they were independent. So I would say they're not independent, they're paired. That's on me. There we go. So they're not independent, they are paired. So I gotta be really careful with my language. Sorry about that. But the rest of this is looking pretty good. I've got my hypotheses. I've got my test statistic, my p-value, conclusion, and 0 should be inside of my interval. Another thing that you have showing up inside of MyOpenMath are a bunch of questions asking if something is paired or not paired. I want to just take a look at a few of these with you to kind of get the hang of it. In general, data is paired if it's linked together, and it's not paired if I have like a different number of samples or if they're unrelated. So comparing pre and post scores of students, that was what we just did in that last problem, and that was paired. So looking at this next one here, assess gender-related salary gap by comparing the salaries of randomly selected men and women. Nothing links those men and women together. That's not paired. Compare artery thickness at the beginning of a study and after 2 years for the same group. That same is important. If it was a different group of patients, it wouldn't be this case. But since it's grouped together, it's paired. Assess the effectiveness of a diet regime by comparing the before and after weights of subjects. If they're the same subjects, that makes that paired. Let's check another one of these out. We'd like to know if Intel stock and Southwest Airlines stock have a similar rate of return. To find out, we take a random sample of 50 days and record Intel and Southwest stock on those same days. That same is linking them together. So they're not independent, they are paired. We randomly sample 50 items from Target and note the price. Then we visit Walmart and collect the price for each of those same items, linking them together. So that makes it paired. If they were different items, just 50 random items at each store, then it would be independent or not paired. The school board would like to determine whether there is a difference in average SAT scores for students at one high school versus another. There's nothing linking those students together. So it's not like these students have been paired up in some sort of a study program. So they are independent students. They are not paired together. I hope this is giving you a feeling for what this looks like for something being matched, paired versus independent. And I hope that calculation for the previous problem was helpful for calculating that test statistic and p-value.